The Tremendous Blast and the Origins of the Universe. The tremendous blast is a thought that has laid out the framework for deciphering the universe. It explains the foundation of current cosmology, according to Einstein's speculation, also referred to as coarse reading cosmology. The immense blast was the moment the universe began its development, marking the emergence of energy and the presence of all matter. This occasion occurred approximately 13.8 billion years ago and led to the colossal universe we observe today. However, recent advancements in cosmology indicate that the colossal blast most likely wasn't the very beginning. Rather, there might have been a stage before the gigantic explosion that was equally important in shaping the universe. This preceding period is referred to as unquantifiable expansion. This development is quite possibly one of the most fascinating aspects of present-day cosmology. It suggests that before the intense heat of the enormous blast, the universe went through an unbelievably rapid and dramatic expansion. During this period, the universe was duplicating in size at a shocking rate. To accurately depict how absurd this extension was, if the universe started smaller than an atom, it would have extended to become incomprehensibly larger than the entire observable universe within a minuscule fraction of a second, around 1/4,000,000th of a second. Though this expansion stage didn't last long, it played a crucial role in forming the universe. When the energy driving this expansion was exhausted, it was released into space, warming it up and producing matter particles that now make up everything we see in the universe. In many ways, this development predates what we commonly think of as the Big Bang. The hypothesis of expansion is now widely accepted in cosmology. However, numerous questions remain unanswered. We still don't know how this development began, how or why it stopped, or how long it endured. These open questions are significant for gaining a deeper understanding of the origin of the universe. Before development, the universe existed in an astonishingly dense, small area of matter, often referred to as a singularity. From this singularity, the initial stages of development eventually led to the formation of atoms, particles, stars, and galaxies. While the potential for the Big Bang to mark the start of everything is intriguing, contemporary cosmology proposes a more complex picture. Some hypotheses suggest that before the gigantic blast, the universe underwent a phase of expansion that caused it to grow at an incredible rate, increasing in size by a factor of 1 trillion in just a brief moment. This rapid extension was sparked by a strange structure of energy that penetrated empty space. When the extension completed, the energy driving it transformed into particles, warming the universe and initiating the hot, dense state we call the Big Bang. This inflationary stage, though cold and empty, set the stage for material production and the universe as we know it. One of the more recent theoretical ideas in cosmology is the concept of eternal inflation. This hypothesis proposes that inflation did not end uniformly, but rather stopped intermittently, creating a variety of pockets, each of which could be a universe in its own right. Our universe may be just one of these patches. According to eternal inflation, there may be an endless number of such universes, each with its own set of physical laws and constants. This is where the multiverse concept becomes relevant. The idea that our universe might be just one among many, or even an infinite number of universes. If this idea is correct, it would explain why our universe is so finely tuned for life. In a multiverse scenario, every possible combination of physical laws could exist in different universes. We just happen to live in one where the conditions are perfect for stars to thrive and for essential elements like carbon and oxygen to form. While hypotheses like the multiverse and eternal inflation are speculative, the idea of expansion itself is grounded in solid observational evidence. The strongest support comes from the cosmic microwave background radiation, CMB, the oldest light in the universe. The CMB was emitted approximately 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form. At that point, the universe became transparent, and this light has been traveling through space ever since. By studying the CMB, cosmologists can essentially take a picture of the universe in its infancy. This light reveals many details about the early universe and supports the inflationary model. One of the most significant discoveries came from the European Space Agency's Planck satellite, which took high-resolution images of the CMB. These images showed subtle variations in the universe's temperature during its earliest days. Remarkably, these variations matched predictions made by inflationary theory. This evidence strongly supports the idea that inflation is not merely a speculative theory, but a key component of how we understand the universe's origins. To fully comprehend the Big Bang and what came before it, two major theories must be unified: Einstein's theory of general relativity and quantum mechanics. General relativity describes the large-scale structure of the universe, including the behavior of galaxies, stars, and planets. Quantum theory, on the other hand, explains the behavior of particles at the smallest scales. Answering fundamental questions in cosmology, such as what the universe is made of and where it came from, requires a theory that combines both frameworks. This unified theory would allow us to understand not just the Big Bang, but also the conditions that caused it. One of the most astonishing aspects of the universe is its size. The farthest objects we can observe are roughly 47 billion light-years away, making the observable universe around 94 billion light-years across. This may seem odd, considering the universe is only 13.8 billion years old. How can the visible universe be bigger than the distance light could travel in that time? The answer lies in the nature of cosmic expansion. As the universe expands, the distance between objects increases, creating regions that are now further away than light could have traveled during the age of the universe. Most researchers agree that the universe extends far beyond what we can see. It's quite possible the entire universe is infinite in size. The observable universe is just the part we can detect, limited by the time it takes light to reach us since the Big Bang. There may be vast regions of the universe we will never be able to observe. Whether or not the universe is infinite, the question remains: is there anything beyond it? If the universe is truly infinite, then there is no outside. The universe would simply continue forever. Even if the universe is finite, it may not make sense to talk about what lies beyond it. Beyond would imply something outside of space itself, which is a property of the universe. So the idea of a beyond may have no physical meaning. Just as the beginning of the universe is a subject of intense study, so is its inevitable end. The best current estimate is that the universe will continue expanding forever, driven by a mysterious phenomenon known as dark energy. Dark energy is accelerating the universe's expansion. Before the discovery of dark energy, scientists believed that the expansion might eventually slow down due to the gravitational pull of matter. There was even a possibility that the universe could stop expanding and begin contracting, leading to a big crunch. However, dark energy appears to be pushing the universe apart at an accelerating rate. If this continues, the universe will expand indefinitely. Eventually, galaxies will drift so far apart that they become isolated from one another. In this scenario, the universe would become cold, dark, and empty. Stars would burn out, galaxies would drift apart, and matter would decay. This ultimate fate is known as the heat death or big freeze of the universe. The story of the universe, from the Big Bang to its possible end, is one of the most profound and complex narratives in science. While we've learned a great deal about the origins of the universe through the theory of inflation and the study of the cosmic microwave background, many questions remain. Why did inflation begin? What caused it to end? What lies beyond the observable universe? Is the multiverse real? And if so, how many universes exist? As researchers continue to study the universe using advanced technologies and unified theories of quantum mechanics and general relativity, we will undoubtedly gain deeper insights into these mysteries. The journey toward understanding the universe is ongoing, and every discovery brings us one step closer. Disclosure brings us one bit nearer to noting the extreme inquiries concerning our existence. The investigation of the universe's beginnings and structure isn't simply a logical attempt. It additionally raises philosophical inquiries about presence, reality, and our position in the universe. One significant topic of cosmology of interest is the nature of dark matter, which is accepted to make up generally 27% of the mass and energy of the universe. Not at all like normal matter, dark matter does not absorb or reflect light, making it both invisible and observable only through its gravitational consequences for noticeable matter. It is fundamental to figure out dark matter for making sense of the development and the evolution of universes. Research and perceptions have provided a few insights into dark matter's properties, but its definite nature remains tricky. Only a few candidates have been suggested, including weakly interacting massive particles, WIMPs, axions, and other exotic particles, but no right-away evidence of dark matter particles has been found up to this point. The search goes on through a mix of terrestrial trials, astrophysical perceptions, and recreations that model how dark matter impacts the enormous scale construction of the universe. One more key area of exploration is dark energy, the secret power driving the sped-up extension of the universe. Dark energy contains around 68% of the universe's absolute mass energy content. Its revelation was surprising and has prompted numerous cosmological hypotheses, including constant and dynamic fields. Understanding dark energy is essential, as it will decide the extreme future of the universe. Researchers are concentrating on its impacts on cosmic structures and trying to figure out whether it remains consistent over the long run or advances. Notwithstanding dark energy and dark matter, investigation of enormous structures' development offers significant insights into the universe's set of experiences. Observations of the immense web, tremendous system organization, fibers, and bunches have demonstrated how matter congregates as a result of gravity, driving the baffling designs. Nowadays, reproductions run on supercomputers help professionals understand how these structures shaped over billions of years and continue to advance. Additionally, astrobiology converges with cosmology as researchers try to figure out the circumstances essential for life beyond Earth. The look for exoplanets, planets circling stars outside our planetary group, has strengthened, with thousands found in ongoing years. A few of these exoplanets are found in their stars' habitable zones where fluid water may benefit from the right conditions to exist. By considering these distant worlds, scientists hope to learn more about the potential for life in a different location in the universe and the factors that make a planet cordial to life. At long last, the job of central cosmology's material science cannot be exaggerated. The mission for a bound, unified hypothesis that joins general relativity and quantum theory continues to confront physicists. Theories like the string hypothesis and quantum gravity intend to link these 2 points, which provide clarification for unusual phenomena like black holes and the beginning of the universe. As innovation drives, so does our capacity to notice and comprehend the vast phenomena of space. Telescopes like the James Webb Space Telescope are altering how we might interpret the universe by providing amazing attention to detail in distant systems and cosmic occasions. With each groundbreaking perception, we move closer to unwinding the mysteries of the universe's arrangement, advancement, and extreme future. The investigation of the universe is a rich embroidery of logical requests and philosophical reflection. From the key powers that shape huge designs to the look for extraterrestrial life, our investigation is a demonstration of humankind's persevering interest in the universe. As we endeavor to answer these significant questions, in doing so, we acquire a more profound gratitude for the immeasurability and intricacy of the universe.